Hello everyone, this is a video for Unit 3 again. This is video 3. I'm going to look at combustion reactions and oxidation and reduction reactions with you in this video. So when we're looking at combustion, it's basically a technical fancy name for burning reaction where we take some sort of hydrocarbon typically and we react it with oxygen and form CO2 gas and water. So this is a type of redox reaction, which is going to be the focus of this video. So a redox reaction is, think about splitting this down the middle here, RED for reduction, OX for oxidation. It's a combination. Two different things have to happen to have what's called a redox reaction. We have to have reduction and oxidation. This is one of those types. If you think about octane in your car, that octane is C8H18. Octane is a hydrocarbon. It's an alkane, and we have it available to us. It is broken apart from extremely long hydrocarbon chain molecules, as you know what happens in a refinery. Hydrocarbon molecules are broken down into propane, which is a 3-carbon molecule, butane, a 4-carbon molecule, octane 8, etc. So what happens when hydrocarbons are burned, combusted? They produce CO2, they produce water, and they also produce heat. So if you were to stand near your barbecue, certainly a butane lighter might feel a little bit warm after it was used. These hydrocarbons react with oxygen, and in order for that to happen, there has to be available oxygen. So essentially in the air. As long as there is oxygen available, the reaction should take place. So now I said hydrocarbons, but it is also possible to have other molecules that contain other atoms. So I said carbon and hydrogen. Well, here's an example of an alcohol. So an alcohol contains carbon, hydrogen, and oxygen. And we know that alcohols are flammable. And so again, typically these are carbon-based molecules, compounds, and the chain is made up of a molecule because of the bonding. And I touched on that previously. Molecular compounds have the covalent bonding, and that was from a previous video in a previous unit. And the products of combustion are carbon dioxide and water, and that is a characteristic. They always form these two products here. So here is ethanol reacting with oxygen, here is methane gas reacting with oxygen, and these are combustion reactions because we have two carbon-based compounds. Each of them react with oxygen, each of them forms CO2, carbon dioxide, and water, and of course these subscripts in front, the 3 and the 2 and the 3 here are all about balancing, whereas the little subscripts, sorry, let me say that again in case I didn't say that correctly, coefficients in front. In case I said subscripts, those are the coefficients. They are for balancing, whereas these small numbers underneath, the 2 and the 2 and the 5 and the 2 here and the 2, these are subscripts. And these are there to show us the chemical formula of each of those. So let's head into what's called redox, into oxidation and reduction. So an overview. Basically, we're tracking what's happening with electrons. So in oxidation, there's an atom that loses an electron, and in reduction, there's an atom that gains an electron. So think about reducing in the sense of gaining a negative makes a number smaller. You can think of it that way. And I'll leave this for you to pause and look at again. So in here, if we had let's just call it element A, it loses an electron, so we will say element A was oxidized, and in this case it looks like A is losing 2 electrons. B is gaining, so B is being reduced because it's gaining 2 negatives. So on a number line, think its charge would get less by gaining 2 negatives. So if it was a charge of +4, it's now a charge of only +2. Its number just dropped by 2 because of the negatives. The positives and negatives add up to give you the charge. When something has been oxidized, we call it a reducing agent. So it's an opposite scenario. And that's because by being oxidized, it allowed something else, the element B here, to be reduced. Same goes for B. B was reduced because it caused, if you will, or encouraged the oxidation of A. You can think of it that way. So it's an opposite scenario. So how do we identify which element's been oxidized, which one's been reduced. So what we do is we have to look at what's happening with the charges, and we're going to look at that more specifically as what happens with the oxidation numbers. So we're tracking the electrons. So any element on its own, potassium here has a charge of 0, chlorine, an element on its own, charge of 0, and here we have K is now +1 and chlorine is now -1. So if K goes from 0 to +1, it lost an electron. It became more positive. So we'd say K, potassium, has been oxidized. Chlorine went from a charge of 0. Again, elements by themselves are not charged. It went from 0 to -1. So it gained the electron from potassium. So chlorine goes from 0 to -1. So it has been reduced. I'll leave you to look at the other two. In order to do this, I'd like you to look at this chart. There are other charts and descriptions in your online textbook, but here is a nice chart that summarizes what are called the rules for assigning oxidation numbers. So how do you know which element in the compound, for example, is in which oxidation state? Like, how are we sure which one lost and which one gained? So as I just mentioned in the previous example, the oxidation state of any atom in its free elemental state is 0. So we go back here, K, in its free state, carbon, notice how there's no charge. However, notice here we've got an ion, so that tin is already 2+, whereas the aluminum has no charge on it. So we follow that as the first rule. We follow in this order. In the second, so you go through and see if there's any atoms in the free element state, they'd have a 0. And then what you want to do is write them above. And the oxidation state of any monatomic, so just one atom ion, is equal to the charge. So for example, tin here, its oxidation state would be this 2+ right here, already indicated. The sum of the oxidation states of the atoms in a neutral molecule have to add up to 0. And if it's many different ions joined together, they have to add up to the charge. And then we start working from group 1, from the far left-hand side of the periodic table, and then we move inward. So all the group 1 metals will have an oxidation state of +1. All the group 2 will have +2, etc. All right. So let's have a look at an example. So there are some examples over here. For the non-metals, we have to look at, what column they're in. And so column 7 is going to be the -1, column 2. So you can think of this as its charge. That does help, but this is per atom. Okay, so oxygen is always -2, and hydrogen's always +1, and fluorine's always -1. And then you can just say everything else in group 7 in the halogens is -1, and everything else in group 6, etc., etc. But hydrogen and oxygen and fluorine, there's no debating those, and you'll see why a little bit later. So let's look at an example here. If I was to follow these rules, okay, so I'm going to follow these rules and make them a little bit bigger here. Follow those. Now, assigning oxidation states, some examples. Bromine. So bromine is one of those diatomic molecules. So it is in its own elemental state. So I see it as, I'm going to write the oxidation number is 0. K+, that is one of the monatomic ones, so that it will be a +1. Now, this one, column 1, we'd say lithium is +1. It's a group 1 metal. Fluorine, fluoride ion, would be -1. Now, carbon, how do I do carbon? Well, I do oxygen first, because oxygen is one of those non-negotiable ones, so it's -2. There's 2 of them, which makes it -4, so carbon is +4, and each oxygen is -2. And then in E, the sum of the charges have to sum to 2 negative, and that is following the rule that is an ion is equal to the charge of the ion. So we would have a 2 negative overall. Each oxygen would be -2. That would be a -8 for O4. So S has to be a +6. So notice that charges are written number and then the sign 2 negative or 2 plus, but oxidation states we write the positive or negative first and then the number. So again, 2 negative is the total. So then if I have 4 negative 2's, that's a negative 8, and then I need a positive 6. So the oxidation is per atom. So oxygen we'd say is negative 2 for 1, and we only write it per 1, and we write S is plus 6. Okay, and so I'm going to go through a few more here. So what's happening in these families in the column 1A, 2A? Remember, A is the representative group. So we're looking at column 2. 2 electrons are being lost. Okay, in column 2. In family 1A, we only have 1 loss. So we have an oxidation state of plus 1. In family 2, plus 2. Family 3, plus 3. And we call those cations. I've gone over those in former videos. When we're getting here into the non-metals, so families 5, 6, and 7, notice that oxygen gains 2, so we'll have an oxidation state of, well, that's actually the charge, so that's actually plus, 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 and I just want to double check this here. It should be written as, and that's a little typo, I apologize for that, it should be negative 2. Like that. It just, I can see that it actually changed, so that too, just bear with me there. Shouldn't be a subscript. It should be so oxidation states are written sign and then the number. Okay, so it should be like that. Sign and then the number. And the charges are written number and then the sign. So I'm just going to quickly change that. So a little bit of work here on the fly, which can happen, and sometimes it has to do with files not saving with the most recent edits. So my apologies on that. So oxidation state is positive or negative and then the number. And of course, so family 7, you see 5, 6, and 7, and those are the anions. So when you're assigning the states, we have to follow these general rules, and they're just all summarized here. Again, just same. I'm just referring back to that chart. And here are all of the answers with some examples of determining the oxidation states. Okay, so how do we do that? Well, I'm following the rules right here, and the rules right back here. So let me just see how much more. All right, so then when you're going through, I'd like you to try these. Follow the examples. So if each oxygen is negative 2, that means there's a negative 6 total in oxidation state, then this one sulfur has to be plus 6. So see if you can follow the rules doing each of those and checking your answers there. I want to leave that with you to do so that I can get through the rest of this little bit, and you can always get in touch with me about any of those former examples right here if you have any questions. So if we have an electrochemical reaction, if we've got an oxidation number changing twice, meaning we have a loss in one element and a gain in the other, then we know we've got what's called a redox reaction. So the number of electrons lost have to equal the number gained. Otherwise, electrons, like atoms, they don't just disappear and they just don't appear. So here's a little summary of what I've gone through here. Is we know that reduction happens if the oxidation state has been lowered because the negative electrons have been gained, and it's acted as an oxidation agent. Exactly, it took electrons from something else, from a different element. In oxidation, the element has lost electrons, so its positive state has increased. So it's acted as a reducing agent. So what more do we need to do here? Here's an example. So here's what's called tracking oxidation numbers. I go and I write the oxidation states per each element. So Mg by itself, 0. Hydrogen, +1. Chlorine, -1. Chloride as an ion. Yes, there's a 2 in front, but we do it per, there's 2 H's and 2 Cl's, but we do it per atom, per ion. So Mg is +2, Cl, each one is -1, and each hydrogen, here we've got H2 is 0. So we know that Mg went from 0 to +2, so it lost electrons. So it was oxidized. And H went from +1 to 0, so it gained. So there has to be loss and there has to be gain in order for it to be a redox reaction. So I'm going to leave this with you to track and see if you, by using the oxidation numbers, putting them all across, tracking the changes to see